And specifically, I'm going to try to focus on like when you should use compute shaders and when you shouldn't. Because they're really cool, they can do really amazing things, but I feel like they're a very specialized tool too. So we're going to get into like why and how that is, and yeah. But before we do that, we have some administrative stuff. So of course, you all probably know at this point that the jam starts this Friday. We have voting. Oh shoot, I should have had that link ready. Oh, I forgot. Yeah, we have voting going on for this jam right now. The plan is to actually switch over the round one voting to the final round voting for the like final theme selection after this meeting. So go to this form if you haven't right now and give your input on round one, so you can influence what theme gets selected for this jam. Because yeah, once this meeting's done, us officers are going to powwow and quickly make a form and send it out for the final round, and then that'll close early Friday, I guess, when we finally select the theme and move over to the 5 p.m. call. So I'm pretty sure everyone, yeah, I recognize literally every name in this call. So I'm not going to waste everyone's time talking about what a game jam is. But yeah, hope to see you all there, and hopefully we get a good theme out of it. Moving on from that, we have, yeah, so like I briefly mentioned earlier, yeah, this is just going to be a talk on like basically when to use, or like what are compute shaders, when can we use that, and I'm just going to skip over like threading and multi-threading and how you can use that as well, because I don't know, I don't have time. I'm starting like a 40 slide deck, so we're just gonna zoom. So before we show off any shaders or do any code or any technical stuff, I just want to give some background info to inform you about like why or like how compute shaders work intuitively, and we can start by doing that. So by defining it, so a compute shader is a program that runs on the graphics card, allowing you basically to offload work that would be running on the CPU otherwise. You might have been to a talk by Shine where he discussed like normal graphic shaders like vert and frag. This is written in the same language, HLSL, but the difference is that a compute shader, as opposed to like a vert shader or a frag shader, it runs completely outside the rendering pipeline. Is it GLSL? Well, I think it depends. I think Unity uses HLSL. Isn't it?
Yes.
I think the acronym's like yeah. So HLSL, it's a little more nuanced than that, but like there's HLSL's built on GLSL, or there's I don't know the exact thing, but in Unity it's written in HLSL for vert and frag shaders and also for compute shaders. That's what we should say. But yeah, they run outside the rendering pipeline, so they're not like inherently tied to the vertices, or like the pixels of a texture. Although you can couple them back together if you want to do something like that. I did not know that. Let's see. And basically the idea of it is because it's on the GPU, it can scale to much larger workloads. And at least in Unity, the compute shader API that they provide is cross-platform. So all the stuff that I will show you today, you can put on like a mobile game or something if you wanted to. And now we must answer the question like, okay, it can scale, but like why the graphics card? What's so special about the graphics card? And I'm sort of just segueing intentionally into this meme. So to compare like the CPU to the GPU, for people who don't know that much about hardware, a CPU basically is a handful of cores, like a single-digit core count. And these single-digit cores are very fast. They're very optimized for doing many things sequentially. First do this, then do that. Lay out a procedure, go down and do it. It's how most people code. Like when you write code, you're usually thinking about, okay, first I'm going to do this. That's line 1. Line 2 is going to be a loop that's going to do actions 2 through 100, and then on to the next thing, one after the other. Whereas the GPU, it has literally thousands of cores compared to the single-digit amount of cores on a CPU, but they are laid out or like optimized at the hardware level to do many of the same thing at once. So yeah, I put a lot of effort into this amazing meme that I made. But the end result of that is if you're doing something in a game where you have a lot of similar things doing similar things, or similar objects doing similar actions, or computing the same thing over and over again, then that sort of naturally lends itself to this parallel computation style of like doing things, where instead of thinking about it in terms of doing this and then this in a defined order, we can instead think about doing things all at once, like just pump it it's like a garden hose versus like a fire hose of data going on. And I know I said we wouldn't talk about multi-threading, but CPUs can do multiple things at once as well using threads. Yeah. Oh, yeah. Shine, we will get to that. Don't you worry, my friend. Yeah. So the CPU can do multiple threads at once as well, but it typically devolves into something called concurrency, which is like I do this thing, but then I might need to wait for something. So while I'm waiting for that thing to happen, I go and do something else at the same time. And that's how you can use a relatively small number of cores to multi-thread. Yeah, we'll talk about the if statements, don't worry. And yeah, but when you scale up to this many cores, 4,000 cores on a GPU, you get parallelism, where we have enough cores to do every task that we could possibly want, unless we're really chugging. And it'll generally just be parallelism. Just do it all at once. Boom. So that's some intuition into the hardware reason for like why why the shader works so fast. And so in terms of code, I created this like color-coded diagram system to hopefully help visual learners understand it in a better way. So imagine we have this code up here on the CPU. This is just a normal C#. We're doing a nested for loop, so we have to do n times m number of this line of code, right? So if we graph this out on like what's happening computation-wise, we might spend this like red amount of time computing f of ij for a given ij, right? And then we do some updating of the memory, right? So we set object of ij, that's the blue part. Object of ij being set equal to the result of f is this blue time. So what's going to happen is it's going to loop. It's going to compute f of ij, put it in the object slot, and then move on. Compute another fij, put it in the object slot, move on. Next, next, next. And this is a slight oversimplification of how it would work on the CPU, because most compilers will like unroll it so that it's... but it'll make minor optimizations, but it's mostly going to look like this. But the idea being that if we could instead compute all of these f's at once in one motion, and then just paste it all into blue at once, or paste it all into object of ij at once, then our execution on the GPU would look something like this, right? So we would say compute f of ij for every I and j, and just send them all to their own core, and they'll get computed individually. It'll take roughly the same amount of time to compute, but since they all happen at once, it basically takes this amount of time, and that's where you can get these huge gains. So wow, like that image was pretty impressive, right? This is pretty small, but really, what is the catch? And believe me, there are catches. You can get caught trying to do these compute shaders. So the first thing that we're going to talk about is that, of course, the algorithm must be parallelizable. Basically meaning, well, I'll talk about exactly what that means. Another important thing for compute shaders is that it only really optimizes the computation time of the algorithm, obviously. So you can have 10,000 actors, right? And you can compute like where those actors in your game are going to go amazingly fast using a compute shader. Their pathfinding can be amazing. But at the end of the day, if they all have a mesh filter and they all have physics systems attached to them and other parts of the engine, those draw calls, that memory they take up, is still going to bottleneck you. So it may just be the fact that computation time isn't your bottleneck, and trying to optimize or spend all this time parallelizing your algorithm and making a compute shader won't actually help you that much. And then this is sort of what Shine and Brennan were alluding to in the No Mic chat. But a GPU core is not a one-to-one thing with a CPU core. GPU cores are very optimized for specific tasks. And like the canonical example of that is that jumps, like you can't really do branching and conditional stuff that well. Basically, and if you want, like, I don't know, do people want me to go into like a hardware reason why that would be? It'd be because CPU pipelines do something called branch prediction. But they have these really long pipelines where for all the instructions that they have to do in sequence, right? When it encounters an if statement, it will try to predict which if branch it's going to go into and compute that ahead of time to save some time in the pipeline while it's waiting for other longer, instructions to pass. And that means that a CPU core will generally be that optimizes CPU performance when you have if branches. And a loop is an if branch, because at the end of the for loop, every time it has to check if I is greater than or equal to length of array. That's an if check. So that counts. Now, that was the traditional wisdom back in the day, but while I was researching this talk, apparently that's only sort of the case still. GPUs have gotten a little bit better at handling these sorts of things. If you're really interested in like what is the performance cost for putting a loop in my shader, then I've linked this, and I'll send the slides over later. You can navigate here and read this great blog post where they test it out. There are some more downsides. That being that there's more to speed than just multiprocessing. Like, just because I can vectorize my whole algorithm, compute it all at once, they have to compute both branches and discard the wrong one. But yeah, that's a detail you don't necessarily need to know. Just know that if branching and looping may hurt your performance, so you typically want to avoid it in your algorithm if you can. But you shouldn't need that many loops, because we're factoring the loops out and doing it in a shader, as you'll see later. But yeah, there's more to compute speed than multiprocessing. There's time for data to travel on the buses between your different hardware components in your PC. So every time that you send data to be processed on your compute shader, it has a travel time, and that is, and if you've taken CSE 351, if you're a CS student, you'd know that it takes a huge amount of time to actually get memory or get data from main memory to the CPU, and that's why we have caches. Well, it's a similar process for sending data over to the GPU. There's also the problem that, if you're running a huge Unity game and you have all these different classes and it's object-oriented and everything, you're going to have a lot of state being stored on the CPU, and your algorithm may use a huge portion of that state. So sometimes it's just unrealistic to copy over like all the state from your game into the VRAM just to do a simple shader call. And there's cache locality. So as you'll see later on, there's this thread group attribute, which is basically just turns into a hyperparameter that you can tune to even further increase or possibly totally ruin your shader. So that there's another confounding variable there to think about. And then this last bullet is personal opinion, but from my observations trying to write compute shaders, there's next to no information out there on it. For example, when I was trying to understand what the thread groups are, they only have like this Windows API developer, like Microsoft doc on it, that talks about what thread groups are. Because ultimately, the compute shader in Unity is just an abstraction over like DirectX 11 or whatever the lower level GPU API is. All right, so going into more detail about the downsides. First, parallelizable algorithm. What this basically means, if you haven't taken a CS class that went over it, is that you can't. Okay, if you're going to spread out your algorithm's computation over many cores, and they're not going to coordinate at all, and there's going to be no defined order, then that order better not matter at all, right? Because if the output of f is dependent on f of the previous iteration, then you have no way to obtain this information at runtime in the shader, right? Because you could be computed before this value or after it, and it's certainly not going to be in memory for you. So, yeah, this can lead to some difficult situations where you have an algorithm you want to optimize, but it's just not clear how you would go about parallelizing it. And this is like a whole field of computer science that is just it's a can of worms. So hopefully the thing you're trying to optimize in the future will be parallelizable. If not, then you immediately fail the check and you can't make it a shader. And then expanding on the time to move data here, just to illustrate it, right? Here's your CPU, it's over here. Here's the GPU right here. You need to send data from like the CPU's cache to the GPU, and that takes time. Just like it costs time to request a file from the disk, like sometimes you open up File Explorer and it just lags. Same issue here, although more optimized, but still there's a cost, and that's what we're talking about. So that's some background info. Now we're going to start talking about like when to use. Given its pros and cons that I've laid out in the background info, when should we use these things? Well, we can reason about it using these diagrams again, right? So, and adding on the info from like this last slide, it's actually a more complicated picture than I first promised, right? Because in addition to the red and blue now, we have this orange, which is actually the time to move from the GPU. And this is just saying that every time you move anything either to the GPU or back from it, you're going to pay a penalty. You pay the troll toll, and it's not always cheap. So keep that in mind before you're... And what that will mean is that you are only going to really want to send jobs to the GPU if they're a really big job, like a really big job, because that's when this doesn't scale that much with... This doesn't scale with the size of the problem nearly as much as this does. So you will get more gains relative to your losses the bigger your problem is. I forgot that I actually had that all written out. So yeah, as the size of your problem approaches a bigger number, the toll becomes cheaper relative to the gains, is the idea. So don't try to use a compute shader to compute a 10 by 10 n-squared algorithm. If your size of the data is only 10 by 10, then that's instantly done on the CPU anyways. So this is like an interactivity point, so you guys can unmute your mic and just be ready to shout out, or you could type in no mic if you want. But just to like hammer that idea home, I wanted to like see if you guys could classify these into shader versus CPU problems. So suppose we have this loop, right? We're looping 10 by 10 times, right? And we're computing f at every step. And every time we call f, it's super fast. It just takes 1 ms. So what would you do here? Would you compute this on the GPU or the CPU? Is the question. Right, CPU, right? Because, again, like this is instant. You can just do that. There's no reason to spend all that extra time busing these 10 pieces of data over to the GPU. What about 100 by 100? Yeah, maybe MS is. I should have used a different second of time. I mean, like, when I say 1 ms, I mean like super small. So maybe I should have changed that to a nanosecond or something. This one, yeah, this one's a little weird. I think that even on an input of like 100 by 100, it's probably not meriting a. It's not going to merit a jump to the GPU. With with 1 ms though, if we take that to be like a long amount of time, or if this was even longer, this is somewhere where you might want to like multi-thread something, spin up a thread pool, and do a couple jobs. What about this one? I give a little hint here. Like, this one would be very clearly GPU, right? Because think logically about what the GPU was originally made to do. The GPU, well, okay, yeah, that's fair, but like the GPU is made to do like pixel number of operations every frame rendered. So if the GPU was made for that type of task in graphics, then it can also be applied at that scale computationally, right? And then I had this weird one where each call takes like 0.5 seconds. And this really is like an example of where it's probably not worth computing on the shader at all. In fact, a shader would probably really, or the GPU would probably really struggle to compute this massive thing. But what you could do is put this in a thread pool and multi-thread it on the CPU or something like that. Okay. So now that I've hammered that home, like, here's like a little flowchart that you could potentially use. But I generally don't like flowcharts because I feel it always depends, right? There are other variables as well. And of course, you shouldn't waste your time optimizing code when you could be building more game. So only optimize if you truly have to. But yeah, can you parallelize it? No, instantly single-threaded. Can you? Yes. Then how much are there? If it's just a few to a medium size, it's not worth the cost. It's just not. And it's not worth the headache, especially, right? That's what this big brain time thing is for. Sometimes it's just not worth it. So just don't do it. But if you have a lot of data to process, you could increase the specs too. If you have a lot of data to process, it's parallelizable, and you're feeling big-brained, then you can try this compute shader out. Yeah. Now, I just want to give I want to get a little more in depth about it. I'm going to give a brief overview of the Unity API for using compute shaders, and then we'll get into the examples. So, what does Unity provide to us to make it easy to do compute shaders? And let's see. I made these slides mostly for people to backtrack to later so that they can have a resource. So I don't know if I'll go over each of these bullet points because it's kind of involved. But basically the flow is that you write a shader, right? We'll show that later. You'll write your shader, you get a reference to it in Unity style by treat it like a prefab and drag it in. You look up the name of the shader. You can look up the shape of the thread group of the shader, which I'll discuss later. You can set the buffers in the shader to send data that is needed for the computation to happen. And then finally, you dispatch it. Right? And when you are moving data back and forth between the CPU and GPU, you use something called a buffer, or a derivative of the buffer class. And what a buffer is it's basically just a big old array of a single data type. And you can make it an array of primitives. You can make it an array of structs, which are like little classes. And you can make them read-write as well, so that you can read and write to them, which is typically what I like to do. So I think most of my examples will use the read-write structured buffer, and that's what you'll probably use for most applications, I believe. But if you want more information on the different types of buffers they offer and what they do, you can try this. You can try this doc I found from Microsoft's DirectX 11 documentation. But like I said, it's kind of hard to find an exhaustive review of like what these do and when you should use them. So regarding like the Unity flow for the buffer, you would instantiate the buffer with the number of elements and the size of the element. That just creates a huge piece of memory that you can do with as you like. You can set the data, passing it an array of data on the CPU side. So this is like a normal C# variable CPU side buffer. It would be an array of vector 3s or something. Then you call the shader dispatch function. And then after that dispatch function is done, you can just call buff.getData. And that will copy data that the GPU filled out during the dispatch and copy it back into that variable. So basically you can data in, data out comes into the same variable, right? And then when done, just be sure to free up the VRAM so you aren't choking your GPU. So to give like some example code, put my money where my mouth is. This is like toy pseudocode, but this is basically what it'll look like. You'll translate a loop into these shader calls, which are basically all just setting up. And then at the very end, when you get data, you can just very quickly loop over. This would be the blue part in the diagram, you know, where like there's a red chunk and then there's a giant blue chunk. This is just copying the data back into wherever you need it for the rest of your game logic to run. And then this is what the shader will look like. See, it has this thread groups attribute. I'll go over this in more detail later. But at every step, you can see here at every step on the CPU, we just call F. But here, it's basically the same thing. You're just setting the buffer equal to F. And then the other thing that we'll have to go over is how exactly how you understand where, like what your INJ value would be at the shader. But because of this ID field, you can determine where in the execution you are, right? So this numthreads attribute, this thing right here, this defines something called a thread group, which I've referred to earlier. So every time you call the dispatch function, the shader.dispatch that I showed, you give it the kernel ID, as in the reference to the unique identifier for the shader in the file, because the shader file that you pass in Unity could have multiple kernels, and you tell it how many groups in the X dimension, Y dimension, and Z dimension you do. So what this means is that if I dispatch 10 groups, 10 X groups, right? Then I will create 10 thread groups of this size for my shader, right? So it actually end up being 10 times 64 by 1 by 1 vector. And what these thread groups allow you to do is it allows you to reason in multiple dimensions if you prefer. So if the computation you're doing is over like a flat plane, it may be easier in your head to index using the thread group. And it basically just changes, like you could do 64 by 1 by 1, or you could do 8 by 8 by 1, right? And it would be the same number of threads dispatched per group. But you would have to change like how you determine your INJ value given the ID. It'd be slightly different logic. And honestly, my tip is just to think in one dimension. Everything is just a vector, and 2 dimensions is just it's a social construct. You don't need 2 dimensions. You just need 1. But sometimes you have to be a little less friendly code-wise, because the shape of the thread group actually does have an impact on performance. It's really hard to find out why or how. But for those who have taken CSE 351, I believe it's for similar reasons that it's basically a cache locality issue where you want all of your data in the buffer to be aligned properly, and you want it to coincide with the block size in like the cache on the GPU. It's a very hardware-y problem. It probably won't matter what your thread group size. So my advice would be to optimize later if your shader's still running poorly. But what I typically do is just make it, 64 by 1 by 1 or whatever. And so, yeah, this will also affect the code. So the other thing that the numthreads affects is the dispatch call, because you want to actually divide by the size of your numthreads so that you have a one-to-one mapping in the GPU back to the CPU, right? You don't want to call, because each group does 64 things, you only need n times m divided by 64 of them. And that's actually what, that's what this function is for, the get kernel thread group size, so that you can dynamically set that on the C# side here instead of hard coding it like I did in this example. Whew. I know I vomited a lot of words at you guys. So now is where I want to get to like the fun part, where we do a simple example. We're gonna work through 3 examples. They're all gonna be related, and we're gonna learn some stuff. So I'm gonna open up my Unity here. Hopefully my Unity will wake up. There it is. Okay. So let's set the scene here. All I have in the scene is this controller. And what this controller is going to do is, as soon as I start this play button, it's going to spawn 128 by 128 game objects with mesh renderers. They're going to be spheres. And I want them to bob up and down in like a sine wave type thing, right? So right now I'm running the code on the CPU, meaning that it's not optimized at all. So let's try it. Right. So you can see here that it's very chunky, right? Like I'm trying to move around the scene right now, and it's just lagging to all heck. Let me pause this. I could do window analysis profiler. Pull this here. Can you guys see all this, by the way? We're good here?
Yeah.
Okay, awesome. Right. So if we unpause this, we gotta run this for a minute. Oh, see, it's so laggy. Look at this performance, right? It's taking forever to compute. Like the script is taking so long. There's garbage collecting going on, and we're just at capacity here, right? So we can try to optimize this. So what I can do here is pull up the VS Code stuff and look at the wave controller class. So here's the starter code where we basically create the ball prefabs and put them in the screen. And here's our loop, right? It's just every update, we're calling CPU wave, and we're saying we need to set the new height of every single, and we need to set the height of every single ball equal to the sine function as a function of time, and where it is in the 128 by 128 square. So it's this n squared 128 by 128 algorithm running every single frame. And we also do some extra work just to make it laggier, honestly. Also updating the color based on the sine function as well. Right? And then, but we can attempt to optimize this using using a compute shader right here. So here you can see, here is the buffer I'm instantiating as promised, getting the kernel index, setting the buffer, setting a couple other variables. You can set other variables, not just buffers, but single variables by name. And then I dispatch it. I dispatch it based on the kernel size right here. And then I get it back. And all I have to do is have this very simple loop updating it again, right? So we can try and test this. by just switching it over to the GPU wave instead of CPU wave every function. Why did I X out the profiler? Let's have the profiler open from the beginning now so we don't lag. Right. And what you should notice here is that it should run a little better, but it'll still be basically horrible and unusable. Right? Because I tricked you. The first example that I showed you, note how you can see even how the cost of the scripts, which is in blue, is actually a little smaller here. But you can see that actually we were so bottlenecked that we couldn't even see how much time that the renderer was behind by. The fundamental problem with this is that this is a bad time to use a compute shader because all of these I shouldn't have exited out because now they disappeared. Run it again. Because all of these balls, every single sphere, is a game object. It has its own allocation. It has its own callbacks. It has they have their own meshes that they have to render. So we basically are stuck at this issue where the computation of the sine function really wasn't that expensive at all compared to the massive load that we were giving. Yeah, this is one of those things where, oh my gosh, ECS is a whole nother can of worms where sort of like multi-threading where you can optimize. But I don't know that much about ECS, but I think that ECS is more like a multi-threaded engine that uses like really good cache locality or something. So yeah, if you have this many actors on the screen and they all take up this much memory and they all have render calls and physics calls, because I left the colliders on these things, I think, it's going to be a complete mess. The shader won't help at all. Yeah. So this is something where the shader is not the type of optimization you want to use. You want to be looking into ECS or something of the like. I have some slides to go over on this topic. So doing a performance algorithm, like trying to reason about like what happened here on the CPU with the shape 128 by 128, right? We can see that the wave controller.update takes 49.61 milliseconds, right? But with the GPU, we do get like a 20% performance gain. We gained like 8 ms right there. So it's doing something, but the main problem wasn't update in the first place, because 49 ms compared to these render calls and all these things, you're gonna have a bad time anyways. So this is decidedly a time when you should choose not to use the compute shader, or if you do, don't expect it to do anything compared to like the other mess that you've gotten yourself into. So yeah, and the other thing that I was going to say here is that really like what also matters here is what the function we're computing over the vector is, right? If we're doing this huge, if we're sending all of this data, like this massive amount of data, all the way over to the GPU, right? We're gonna do the bus thing. We're gonna spend some orange time, but the computation of f is so small anyways because it wasn't that difficult to calculate in the first place. Then your gains are going to be relatively lower, right? Those two calls to sine, even though I added the color thing, doesn't really put a dent. I didn't see the update state. Is the renderer using material property blocks or just setting material color? I'm literally just setting the... I think I do a material.color. I'm doing something. I'm updating the meshes materials color, the mesh or the mesh renderers filters color. Okay. But yeah. So basically, two things went wrong. A, there's way too much stuff going on in the other parts of the engine to optimize out. And B, the thing that we were trying, the algorithm that we were computing, just wasn't that expensive. So let's give it another crack, right? Let's optimize this by just, instead of having individual game objects and meshes, we're going to do the same computation, but all on one mesh. So what I have in this controller is a slightly different class. it creates a custom mesh with it calculates its own vertices and stuff, and then it repositions the vertices. So this is actually just exactly a normal shader that you could put on a material. But I'm doing it in Compute Shader to demonstrate the difference, right? So here's the CPU, right? We have this sine wave mesh thing, and we're updating the colors as well. And you can see that it changes over time, so it's the wave is moving, right? And if we look at the performance analysis here, general analysis profiler, right? You can see that even on the CPU, it's actually performing pretty well, right? But it's going to perform even better on the GPU. I keep Xing out the profiler like an idiot. So now it's running on the GPU. Window, analysis, profile. And now look at the difference. Oh my gosh, let me pause the game. Let's go back. Can I go back? I don't actually know if you can go back that far in the profiler. Let's do this again in slow motion, okay? Right. Here's my terrible CPU code. Oh, wait, I gotta open the profiler again. What is it's Control 7. Control 7. Open this up. You can very clearly see that here the update call is taking like 22 ms per second, or per call, right? Oh, I keep Xing it up. You know what? I have a slide made for this explicit purpose, right? Here's the call to the CPU, and here it is with the optimization on the GPU. You can see that we actually cut it down from taking 21 ms every frame to just 4.4. So now that we've removed this confounding variable, we can see that actually there is a huge speed up in computing the sine wave on the GPU instead. And you can only imagine how much better this is if instead of computing the sine wave, we're computing this like really expensive noise function or something, and we're trying to do terrain generation or something. Wink, wink. And on that note, doing it that way generates a new material for each rendered instance. Oh yeah. I might have actually updated the color a little inefficiently. But yeah, this is interesting. We can very clearly see that the compute shader is doing what we want it to do, right? But it's kind of a toy example because it's not really doing something useful. So what I wanted to demonstrate with this final demo is a third controller, right? But what this thing does is it actually, instead of using that sine function for our f, I just replaced it with a noise function, like a Perlin noise or something. And what I'm also doing is, because this is supposed to be like a toy terrain generation example. So what I'm going to do here as well is, even though we're just creating the mesh for the top layer, which is like 128 by 128 chunk, I want to simulate as if we're like in Minecraft, and we have to generate not only the first layer, but like an entire underground. So it's actually 128 by 128 chunk times the height, which in this case we could set to 8 or anything like that. And then I actually have some extra code on the main camera to do some basic map gen. So basically wherever I move, just keep generating chunks around me to keep filling in the space, right? So this is a more practical game example where compute shaders are really cool and nice. Because if we run this on the CPU, note that this is the CPU. Oh my gosh, here we are. Now, forgive my noise function, because honestly, I didn't have time to make a really good map gen noise function. I just pulled this really terrible noise approximation function off of GitHub because it was super easy to code into the shader. But yeah, here's the noise. We're generating terrain. Like, imagine this is like a really high bird's eye view of like the mountains or something, right? And as I move forward, you can see it sort of freezes as it has to generate more chunks around me, right? But look at all these computations we're doing, right? Of course it's going to freeze. We're on the CPU. And I'm on a Threadripper, by the way. Right? all these things that I'm showing you, this is on a 16-core CPU running at 4 gigahertz. So if it's buckling on my CPU, oh my gosh, my code gen, that's an embarrassing bug. But yeah, I'm flexing my computer just to show you what a difference this is going to make. Because now we're going to compute it on the GPU instead. Boom. Here we are, same generation. Oh, gorgeous. Look at this. You could fly for days. You could generate as many Minecraft chunks as you want, and it doesn't matter, right? Because the shader really pays off the greater the scale, right? The bigger the mesh you're trying to change, the faster you're trying to do things, the more that the things like these shader can matter, right? So yeah, I think that this is a really impressive, like, good example of like when you would want to use a compute shader and how much it can help. I mean, just look at how fast. Let's do it. Let's do another CPU run, right? Let's take a look at this. It takes forever to load, first of all, and look at this. Are you kidding me? Would you put your kid on this Minecraft game? Would your kid watch YouTube? Would he watch PewDiePie play this game? I don't think so. I don't think so. Right? And that's with some baby depth, too. I can't even show you CPU on a higher depth, but we can just double that and stick it on the GPU. What's the worst that could happen, right? Immense flex. Immense flex. The GPU is just so much better for this job. This is when you use compute shaders. This is when you get the power, right? And I hope that with that, you guys can understand the power of compute shaders. Yeah, I have. Yeah, and that's it. I just wanted to end the talk on that note. So, are there any questions? Does anyone? Oh, I forgot to show the code for parts 2 and 3. So I guess we can briefly go over that. So let's see. Here is the compute shader for the noise function. You see all I'm doing here, it's this normal, here's the kernel. Here's my numthreads, right? And all I'm doing at every step, I even have a for loop. I even broke the rule. I even broke the rule in my shader and used a for loop, even though I'm not supposed to, because that's conditional branching. But I did it. And so this is for each of like the 8 or 16 layers, right? All it's doing is it's just computing this new float 3, saying the vertices X position stays the same, its Z position stays the same, and its Y position is just this function, right? It's just this call to the noise function. That's it, right? And here's my noise function. It's a terrible noise function. It doesn't create good-looking like Minecraft generation at all, but it is very simple and nice, and you can tune the parameters to change how it looks. Yeah, so that's the shader. And then, of course, on the terrain controller, this is what every chunk game object uses. Here's what it's doing, right? We set the buffer equal to the initial state of the vertices. We don't even need these anymore. This is because I copy pasted the code from the wave controller. We don't need amplitude or or even time anymore. But I'm setting the offset of this object so that we can do good continuous noise. And I'm setting the row length and the calculation multiplayer and just sending over some good information. And then I dispatch it, and then I read it out the other end, and that's it. It's that easy. It's literally a direct translation of the CPU code. Yeah, you could do that. But then you get, like in Minecraft when you run too far ahead and you're basically flying over void because they haven't genned in yet. That would be the difference, is if it was async, right? Is you would expect it to be there, but you could just fly right over it, honestly, and it would still be running to catch up. Better to just optimize it so it just instantly runs, and then maybe async it. Are there any other questions? Or does anyone have any question about any of this code? Do they want to see a specific part of how anything works? Because I'm totally free to just go over this for however long I need to. I'm totally free. No? Okay, cool. Then, yeah, that's a good point, Shane. Yeah, that's everything I wanted to cover today. Hopefully that gave you like an intuition into A, what compute shaders are, B, how they work a little bit, at least a good intuition for it, and C, most importantly, when should I use it? Because that's like the hardest thing to decide when you're trying to optimize your games. Where should I look? What should I try? That's some intuition into it. Cool. That's all I got.
Whoa!
That's
Woo!